Imagine sitting down to play a high-stakes game of chess,
Okay.
and your opponent has absolutely no idea what chess actually is. Like, they don't know what a board is, they don't even know they're playing a game,
Right.
and yet they beat you.
Yeah, which is terrifying on its face.
Exactly. So today, for you listening, we are answering one single massive question. What is actually happening inside the brain, quote unquote, of an artificial intelligence?
And I mean, that question is really at the core of a massive cultural anxiety right now, you
Yes,
know?
absolutely.
We look at our phones and our computers and we're just constantly confronted with these headlines swinging wildly between like AI being a glorified autocomplete and then the next day it's an existential threat ready to take over the planet.
Yeah, the whiplash is real. But we are going to cut through all of that modern hype today. Our mission for this deep dive is to take a massive step back.
Hmm.
We're pulling from some really illuminating excerpts in the book, Simply Artificial Intelligence, published by DK. And we want to trace this technology back to its absolute roots.
Yeah, down to the literal mechanical nuts and bolts of how a machine supposedly thinks, just to find out what it actually is.
Right, because looking backward is really the only way to understand where this technology is heading.
Definitely. And the sources make it super clear that this isn't some brand new Silicon Valley obsession.
No, not at all.
The history of AI is actually a surprisingly long, deeply human history of trying to build a living machine.
That phrase, living machine, it completely reframes things for me.
Yeah.
Yeah, because you tend to think the anxiety about artificial minds started when, I don't know, someone plugged in the first early computers in a lab somewhere in the 50s.
Right, yeah.
But our sources trace the concept of forged artificial life all the way back to the mythology of ancient Greece and China.
It's wild. Human beings were telling stories about artificial life long before we had the actual tools to build it. And then by the 18th century, engineers started turning those ancient myths into physical reality by building what were called automata.
Okay, yes. These were those wildly complex self-propelled devices,
Yeah.
right? Like a mechanical figure that could write a letter or play a musical instrument.
Exactly. They were completely powered by gears and springs, but to people back then, they looked like magic.
Right.
And the distinction between those early clockwork machines and what we build today, that actually defines how we categorize AI.
How so?
Well, in the language of our sources, an automaton is a computer program to perform a highly specific task. So, forecasting the stock market, for instance, that's the modern work of an automaton.
Okay, got it.
An android, on the other hand, is specifically something designed to mimic human behavior.
Okay, let's unpack this for a second. Because if an automaton just runs a specific task, then a modern recommendation algorithm, like the code serving you videos on your feed right now,
Yeah.
is really just the digital equivalent of an 18th century wind-up clockwork toy.
Yeah.
Like, it's incredibly complex, obviously, but ultimately it's just following a fixed, predetermined mechanical track.
The sources point out that in many ways, they are exactly that. Current AIs are highly sophisticated, and they appear to have minds of their own, but none of them can actually control their own actions yet.
Right.
We are essentially looking at incredibly advanced clockwork. And building an automaton clearly highlights humanity's long-standing urge to replicate itself.
Yeah, definitely.
But it raises this vital question. Just because a machine flawlessly mimics life, or mimics a human action, does that actually make it intelligent?
Which forces us to sit down and pin down what intelligence actually is.
Right, exactly.
And the text shows how much our definition has evolved over time. Like Alan Turing, one of the foundational figures in computer science,
Yeah.
he originally focused his tests for machine intelligence heavily on numerical and mathematical capabilities.
Right, he held a very specific narrow view of what being smart meant.
Yeah.
Modern scientists, however, they argue that intelligence is fundamentally fractured into at least 8 distinct kinds.
Okay, let's slow down and look at that list because it is fascinating.
It really is.
They break it into linguistic, artistic, numerical, sensory, meaning how you interact with your physical environment, spatial, emotional, physical, and reflective intelligence.
Right.
And reflective being the ability to actually look at your own behavior, analyze it, and modify it going forward.
And when you look at all 8 side by side, the contrast becomes stark.
Yeah.
Because a calculator is mathematically brilliant. It vastly outperforms a human in numerical intelligence, but it possesses zero emotional or reflective intelligence.
Right. We can all agree a calculator isn't conscious.
No, definitely not.
But the text introduces this philosophical theory called computationalism that makes this incredibly dense.
Yeah, computationalism makes a really bold claim. It argues that all thinking, whether it happens in a human head or an artificial machine, is fundamentally just a process of using algorithms to convert symbolic inputs into symbolic outputs.
Wait, so this theory asserts that my brain, your brain, the listener's brain,
Yeah,
we are all just wet computers.
pretty much, yeah.
But if I'm following a recipe to bake a chocolate cake-like, I take the input ingredients, I follow the algorithm of the recipe, and the output is a cake. Does that make the recipe itself a mind?
I see where you're going with that.
I mean, I have to push back on that. It feels far too clinical to say human thought is just a recipe.
It does feel reductive. To a computationalist, though, the underlying mechanics of thought are strictly data processing.
Okay.
And the sources introduce a concept to explain this called multiple realizability.
Multiple realizability, what is that?
It's the idea that a computation doesn't actually care what hardware it's running on.
Hmm.
Think of it like the melody of the song Happy Birthday. You can play it on a grand piano, you can hum it, or you can plunk it out on a cheap kazoo.
Right, so the physical hardware changes.
Yes.
But the algorithm remains exactly the same.
Exactly. And the implications of that are profound. An algorithm is just a set of logical steps. You can run those steps using the 86 billion biological neurons in a human brain, or you can run them on an electronic artificial brain made of silicon.
Wow.
To the computationalist, the medium just doesn't matter. The argument is that if the human brain is just a biological computer, then one day an AI could eventually possess genuine human-like consciousness, not just a simulation of it.
Okay, so if we accept the premise that thought is just a sequence of logical steps to get a definite answer, the immediate historical roadblock becomes obvious.
Which is?
Humans are terrible at doing thousands of repetitive steps without making a mistake.
Yeah, we get bored. We get tired.
Right. So how do we move from a philosophical theory to actually forcing a machine to do the grunt work?
Well, the search for a physical machine brings us to the 19th century and an inventor named Charles Babbage.
Okay.
He designed the analytical engine, which was intended to be this massive, programmable calculator.
And the detail in the text that blew my mind is that Babbage was inspired by the textile industry.
Yeah, the looms.
He looked at Jacquard's silk looms, which used these stiff pasteboard cards with holes punched in them to dictate the incredibly complex patterns woven into the fabric.
And Babbage realized those punched holes could be used to store mathematical instructions for a calculating machine.
That is just brilliant.
It is. He designed an architecture featuring a separate memory unit and a processing unit.
So for you listening, think about that. Every time you hit save on a document today or you download an app, you are utilizing the direct evolutionary descendant of a 19th century weaving machine.
It's crazy to think about.
It really is. The tragedy, though, is that Babbage's engine was never built in his lifetime. It just remained gears and levers on paper.
Yeah, it was mechanically way ahead of its time. But that theoretical groundwork paved the way for Alan Turing in 1936.
Right.
Turing proposed what we now call the universal machine. And like Babbage's engine, this wasn't a real physical box you could touch. It was a thought experiment.
Turing imagined a machine with a read-write head moving back and forth over an endless paper tape.
Exactly. And that tape was marked with binary coordinates, so just zeros and ones.
Okay.
Turing understood that those two digits could represent literally anything. They could be mathematical instructions, numbers, letters of the alphabet, or even just the electrical states of on and off.
Let's visualize how that actually works, because
Yeah.
it's so fundamental. The imaginary machine reads a 0 on the tape. Based on its internal algorithm, it knows exactly what to do next. It might move one space to the left, erase a 1, and write a 0.
Right.
Just by sliding over that paper and flipping those two numbers, it can calculate anything.
Yeah, and the absolute peak of this paper computing era is the Turing algorithm in 1948.
This story is amazing.
Turing and a colleague essentially wrote a complete algorithm for playing chess. The problem was, electronic computers powerful enough to run it didn't exist yet.
So what did they do?
Turing acted as the computer himself. He read through the algorithm on paper to calculate each move.
It's like writing the ultimate, incredibly complex video game code on a napkin decades before the television was even invented.
It really is. And by acting as the computer, Turing proved that highly complex calculations can be performed purely by following a rigid set of instructions, step by step.
Right.
With the machine needing absolutely zero understanding of the task, the piece of paper doesn't know it is playing chess.
It's just following the arrows on the napkin.
Exactly.
Babbage and Turing proved definitively that hardware and software can be completely separated. You just need a universal language, which is binary, and a physical machine capable of reading those ones and zeros fast enough.
Which brings us to the moment we finally take those imaginary paper tapes and electrify them into modern computing.
Finally.
And the sheer physical scale of these early machines is staggering. We have to look at ENAC, which was built between 1943 and 1946 in the U.S.
This machine was an absolute monster. 18,000 vacuum tubes. It filled 1,800 square feet of space.
Huge.
It was designed to calculate artillery range tables for the military. And a complex calculation that would take a human days was finished by ENAC in 20 seconds.
Yeah, but the drawback was the programming process.
Oh, right. Imagine operators physically walking around this massive, sweltering room, unplugging heavy cables and replugging them into different slots just to change the math problem. That sounds like a nightmare. The physical connections themselves were the software. The physical exhaustion of moving thousands of cables just to run a new calculation is hard to wrap your head around. But then John von Neumann steps in.
Yes.
He architects a new blueprint.
Right. Von Neumann basically said, let's stop rewiring the entire house every time we want to turn on a different light bulb.
Makes sense.
So he split the architecture in two.
He created a memory side to store the instructions and a central processing unit, or CPU, to actually execute them.
Exactly. The CPU decodes instructions and handles the math. By storing the program in the machine's memory, you didn't have to rebuild the physical connections in the room anymore.
That leap made machines easily reprogrammable through software rather than physical labor.
Yeah, it changed everything.
And for you listening right now, pull out your smartphone or look at the laptop you're using. They're running on the exact same von Neumann blueprint figured out in the 1940s.
True.
Memory over here, CPU over there. The basic architecture hasn't fundamentally changed, it just shrank.
Yeah, but while the architecture shrank and became exponentially faster, other scientists were tackling a totally different problem.
Okay.
How to make the logic inside the machine operate more like a biological brain. Which brings us to Walter McCulloch and Walter Pitts in 1943.
The inventors of the artificial neuron.
Exactly. They created what they called threshold logic units, which were electronic mechanisms that closely mirrored how human nerve cells operate.
Okay, so how does an artificial neuron actually work in practice without sounding like, sci-fi jargon?
It's simpler than it sounds. Imagine a tiny electronic processor. It receives electrical signals as inputs, very similar to a biological neuron receiving signals from other neurons.
Okay.
Now, each of those input connections has an associated strength, which they called a weight.
So some inputs matter more than others. Like a heavy weight means that specific signal has a louder voice in the calculation.
Exactly. The artificial neuron takes all those inputs, multiplies them by their specific weights, and adds the total together.
Got it.
This is where the threshold is crucial. If that combined total crosses a certain predetermined number, the threshold, it triggers an activation function, and the neuron sends out its own signal.
And if it doesn't?
If it falls short of the threshold, it just stays quiet.
So it's a mathematical tipping point. If enough heavy signals hit it, it fires.
Mm-hmm.
Just like a nerve cell in our own brains reacting to a stimulus.
Precisely. By mirroring the brain's biological structure electronically, McCulloch and Pitts laid the literal groundwork for modern neural networks.
Wow.
The foundation of everything we call AI today relies on massive interconnected webs of these artificial neurons passing signals to one another.
Okay, so we've gone from ancient Greek myths to clockwork automata, to paper algorithms, to giant rooms of vacuum tubes, to artificial brain cells.
It's quite a journey.
It really is.
Yeah.
And that sets the stage for where we stand today, because the sources highlight a massive shift in how AI is actually trained now.
Yeah, for decades, AI research focused on classical or symbolic logic.
Right.
It was based on explicit rules, like, if this happens, then do that. But eventually, researchers realized they couldn't write enough rules to cover every complex situation in the real world.
So they changed tactics.
Exactly.
Right.
The focus shifted to machine learning.
Okay, so instead of programming explicit steps, you take massive data sets and use them to train these models to perform tasks on their own. But how does the machine actually learn from that data?
Well, it's a process of trial and error using those artificial neurons we just discussed.
Mm-hmm.
If you feed the network an image and ask it to identify a cat, it makes a mathematical guess based on the data passing through the network.
Okay.
If it's wrong, the system receives feedback, and it mathematically adjusts the weights and threshold of all those tiny artificial neurons.
It tweaks the knobs until the math aligns perfectly with the visual pattern of a cat.
Right. It learns through constant, rapid adjustment.
That's wild.
But it is vital to clarify the terminology here because this statistical pattern matching is where public hype gets totally disconnected from scientific reality.
Oh, definitely.
We really need to distinguish between weak AI and strong AI.
Okay, so if weak AI is the chess-playing paper tape, strong AI must be the holy grail, a machine that actually checks off all 8 boxes of intelligence we talked about earlier.
Right.
But what constitutes weak AI exactly?
Weak AI refers to machines capable of specific, limited tasks. Playing chess, translating languages, diagnosing a medical scan, or generating an image.
Right.
It might do that one specific task better than any human on Earth, but that is the absolute limit of its capability, and the text is unequivocal. Weak AI is the only kind of AI that exists today.
Wait, the only kind?
The only kind.
So what does this mean for our daily interaction with this tech? Like, when I go online and a machine learning model writes a highly emotional sonnet for me, it's not actually demonstrating artistic or emotional intelligence.
Nope. It is a weak AI using massive amounts of data to simulate artistic intelligence.
Oh, wow.
Yeah, it's statistically predicting patterns based on the thousands of poems it was trained on. It doesn't know it's writing a poem any more than Turing's piece of paper knew it was playing chess.
Okay, that puts a pin in a lot of the sci-fi panic.
It really does.
Because if that's weak AI, then strong AI, the machine that possesses linguistic, spatial, emotional, and reflective intelligence, that must be entirely theoretical.
Strong AI remains just a concept right now.
Mm-hmm.
If it is ever achieved, its defenders argue it might actually possess human-like cognitive abilities and genuine consciousness.
Right.
But we are incredibly far from that reality. A machine churning through data to find statistical patterns is fundamentally different from a machine possessing reflective, self-aware intelligence.
Which brings us full circle.
Yeah.
We started out trying to understand if we should be terrified of our smart speakers or if they're just glorified autocompletes.
And the historical context tells us they are highly advanced automata. They are profoundly useful tools, but not yet conscious minds.
Well, we've covered immense ground today. From the ancient myths of living machines through the clockwork toys of the 18th century, we saw Babbage, inspired by silk looms to design programmable memory, and Turing proving on a simple paper tape that you could separate hardware and software.
Yeah.
We saw those ideas electrified in the massive vacuum tubes of ENIAC, streamlined by von Neumann's architecture, and modeled after our own biology with artificial neurons.
It's been a long road.
And we arrived at the reality that today's AI, despite all the magic it seems to perform, is still an incredibly fast, data-driven calculating engine, not a rival human mind.
Because the physical mechanics of computation are complex, but they are ultimately just algorithms running on specialized hardware.
Right. But I want to leave you, the listener, with one final thing to ponder, building on everything we just discussed.
Okay, let's hear it.
If the theory of computationalism is actually correct, if our human brains really are just biological computers processing algorithms, what happens if we do eventually build a strong AI? If we construct a machine that perfectly demonstrates all 8 types of intelligence, how will we ever be able to prove whether it's actually experiencing true consciousness on the inside, or if it's just the universe's most flawless, impossibly complex imitation of a wind-up clockwork toy?
Wow. Yeah, that remains the ultimate unanswered question of the living machine.
It really does. Thank you so much for joining us on this deep dive. We'll catch you next time.